Our previous lessons have provided you with an overview of drill rigs and basic tools for excavating, such as augers and buckets. In this lesson, you will learn about some of the more advanced tools that are commonly used to drill through rock or other hard materials. The methods we'll describe include core barrels of various types, including single and double wall core barrels, and we'll see why that aspect is important, and other full face excavating tools, including percussion drills and full face rotary reverse circulation drills. Finally, we'll briefly touch on hand excavation, which is not too common but still used on occasion. Core barrels are one of the first options considered for rock which is too hard for rock augers to be productive in drilling. Core barrels may also be used to advantage when uneven material is present at the base of the excavation, such as where large boulders are encountered or rock with seams or voids. The core barrel can help to keep the hole going straighter than an auger, which can be more easily deflected to one side or the other. By coring the rock, the crowd of the drill rig is applied only to the perimeter instead of across the entire face of the rock, and thereby concentrates the force on the teeth around the perimeter. It may even be possible to remove rock in large pieces without having to cut the entire surface. The simplest form of a core barrel is a single wall steel tool with a single row of teeth around the perimeter, as you see here. The teeth are positioned to be towing slightly inward and outward in a staggered pattern so as to cut a slot that's slightly larger than the thickness of the core barrel. The teeth are also inclined to promote the removal of cut material from the slot, although a single wall core barrel does not have a direct means of removing cuttings from the face. These single-walled core barrels are fitted with shark's teeth type points as might be used for soft or decomposed rock. These teeth are fitted with hardened high carbide steel on the face of the points to resist wear. This photo shows a core barrel with the pointed bullet or plumb bob teeth, as were shown previously on many of the rock augers. These teeth are more effective in harder rock. Notice the staggered pattern in the position of the teeth. You can see in the photo how the core barrel cuts a slot around the perimeter, leaving the interior rock intact. Very often, this cut provides a stress relief around the perimeter, especially for fissile flat-bedded rocks like shales or mudstone or sandstone, and then a rock auger is used to excavate the center. The core barrel thus facilitates the rock auger excavation. Occasionally, the contractor gets lucky and an intact core breaks off nicely and is snagged into the core barrel, especially if the rock is hard and horizontally layered, has fractures or weak seams, like the limestone in this photo. This photo on the right is from Nashville, Tennessee, where the limestone frequently contains voids or weak seams, and so it is often necessary to penetrate through fairly strong rock in order to achieve bearing at a depth where the rock is more continuous and sound. This is a project in Minnesota in which a relatively intact sandstone was retrieved pretty nicely with a single wall core barrel. If an intact core doesn't break off and cannot be retrieved, it might be necessary to break up the core using a chisel or another percussion tool, then change the tools to a rock auger or a grab to remove the broken rock pieces. In these photos, the sandstone core is snagged with a core barrel but wasn't easily removed from the tool. So you can see the guy with a hammer, he's trying to help get the core out. Rock cuttings can sometimes bind the core within the barrel, or it can just twist and get hung. It's not uncommon with coring that the time spent actually coring the bottom of the hole is less than the total time spent retrieving the rock afterward. You can see chunks of irregular rock lying in the foreground. Double-walled core barrels offer the advantage of the ability to circulate fluid within the cut to remove the cuttings and allow more effective cutting. The double-walled core barrel on the left includes pointed rock teeth and 5 ports for circulation of fluid. The fluid is pumped down into the cutting surface and flushes the cuttings up alongside the core barrel, generally along the outer surface in the space provided by the overcut from the bits. The flushing fluids normally are air, although often working underwater. So these tools generally require steel casing to be seated into the top of the rock to provide stability of the overburden during drilling and contain the drilling fluids. Notice that the core barrel on the left is equipped with rock bullet teeth, and the one on the right has roller bits. Roller bits are typically used for harder rock. In the closer photo of the roller bit, you can see the hardened buttons that are intended to concentrate force at a point and crush the hard rock at the point of contact. Less brittle rock may be less effectively drilled using these bits than with teeth. The rollers must have fluid circulation to both cool the bit and flush the cuttings away, or else the bit will continuously grind on the cuttings without effectively breaking fresh rock. The effectiveness is very much related to the amount of pressure applied at each contact point on the rock, as well as the behavior of the rock under this stress. You can see that the crowd from the rig is distributed onto the rollers. The more rollers, the less downforce each individual roller will have because of the limited crowd from the drill rig. However, too few rollers, and they are too widely spaced, they can catch a seam in the rock and get broken off of the core barrel. So the design, selection, and use of the optimized use of these tools is a bit of an art form, but the contractor must have good information about the strength and other characteristics of the rock. Since double-walled core barrels include fluid circulation to flush the bit, the cuttings at the bit need to be returned and collected somewhere. That normally occurs with some type of a catch basket on top of the tool. The roller-equipped core barrel in this photo includes what's commonly called a calyx basket at the top, which is used to catch the cuttings as they are flushed from the bit by air or water. The fluid will have enough velocity to convey the cuttings around the bit and alongside the core barrel itself, but when the fluid reaches the full hole diameter above the tool, the velocity will drop and the cuttings will drop out. The lowermost section of the core barrel tool has a plate across the top, and the uppermost portion can be lifted separately to open a space between the two and allow the cuttings to be removed. So here's a photo showing this tool as it's coming out of the hole with the cuttings visible in the container at the top in the photo on the left. So let's look at an example of the use of a core barrel from the construction of the Stan Musial Veterans Memorial Bridge in St. Louis. This project is a new cable-stayed structure that carries Interstate 70 across the Mississippi River and is founded on large diameter drilled shafts that are socketed into a hard limestone, some of which is visible from an extracted core there in the photograph, in the foreground of that photograph. From a design standpoint, one might ask why you would be drilling a hole into rock that is as strong as the concrete that will be used to fill the hole. That's a fair question, because if the load on the foundations were simply axial compression, it would make no sense to be drilling rock other than to seat the foundation and secure good in-bearing surface on it. But for bridge pier locations in the river, at this site, all of the soil above the limestone is subject to scour, and the foundations must provide lateral resistance for wind, vessel collision, and seismic loading on the bridge. It's close to the New Madrid fault zone. So these large drilled shafts had to be drilled into the rock about 15 to 20 feet. And except for their large size, these foundations illustrate typical use of a double-walled core barrel in rock. The hole is cased down to the rock and filled with plain water, and the water kept at a level higher than the river in order to minimize risks of inflow around the bottom of the casing. You can see how the circulation of air through the core barrel is used to flush the cuttings away from the roller bits, and these cuttings will be caught in the calyx basket. You can also see that the core barrel is being rotated in both directions to achieve a clean cut around the core and keep the cuttings flushed away from the face. After the core barrel is extracted, the calyx basket is dumped by lifting the top can off and rotating the tool in the water to wash the cuttings off. In this case, at this site, the rules allow discharge of anything coming out of the Mississippi River to go back into the river, so they didn't have to contain these cuttings. That's a bit unusual. On most projects, the cuttings will probably need to be contained if you're over water in a barge or tank of some sort, or just discharged onto the ground and scooped up with an excavator or a loader if the job were on land. On this project, the cores were not recovered in the core barrel itself, but rather with a special hydraulic tool that was lowered over the core, used to break it off, and then the hydraulics, besides breaking it off, pinched down on it to capture the core. This tool was made by the Stephen Hayne Company from Texas, who specialize in tooling and equipment for large diameter drilled shafts. Cores were quite heavy, and the lifting crane was at its limits to remove cores that are even a few feet thick. A key factor in the successful coring and extraction was a thorough geotechnical exploration. There was a boring at each foundation location that revealed the locations of existing horizontal fractures and seams, so the extraction of the cores could be planned to coincide with known breaks in the rock. You can see the cuttings on top of the core from flushing around the bit that occurred on the inside between the core barrel and the intact core. The cuttings flushed to the outside and went up into the calyx basket, and the cuttings that were flushed to the inside ended up deposited on top of the core. If the core cannot be extracted, or if boulders are encountered that start rolling around and can't be cut effectively, then an old-fashioned chisel might be employed to break things up so that a tapered auger can get the pieces out, or a grab. This tool is simply lifted and dropped in a brute force attempt to break the rock into pieces. A boulder or a large chunk of rock can be particularly difficult to retrieve if it's too large to snag with an auger or other tool and rolls around in the hole so that you really can't cut it effectively. No contractor likes to have to use a chisel because it's so slow and tedious, but sometimes it's the only way. So here's a photo of a large chisel, which you can see contains a breaker bar across the bottom to concentrate the force, and a heavy weight to give it a lot of impact force. This is a very heavy tool, and it requires a substantial crane even to lift it. So these photos are from the Selwood Bridge project near Portland, Oregon, where drilled shafts were constructed using an oscillator and a grab system, as you can see in the background. The drilled shafts were excavated through a stratum of sand, gravel, cobbles, and boulders, and founded into either the Troutdale Formation, which was a cemented layer that also contained cobbles, or into a basalt bedrock, which some holes penetrated into, and the basalt was very irregular and weathered on top. The large chisel in the foreground was used to break boulders and also break up the Troutdale or the basalt so that the hammer grab could extract the material and extend the foundations down into the bearing layer. These foundations relied on both side and base resistance within the bearing layer.